Hopefully this thing's ready too. So welcome back to the afternoon session, everyone. I'm pleased to introduce Carissa Slone from Rochester, who will tell us about the slices of sigma ℕZ over Q8. Thanks, Chris.
There you go.
All right, there we go. Is that better? All right, so first up we've got some background. Sigma is the one-dimensional sign representation of C2. So what I have here is a copy of R, which I'll call R sigma. And what sigma does is that it acts by flipping. The regular representation of C2 is then rho C2, which is 1 plus sigma, where 1 is the trivial representation of C2. And then S sigma is the one-point compactification of R sigma. We're going to be talking about various groups today, including Klein 4. So of course we want to know about the representations of Klein 4. It has 3 sign representations. They are the pullbacks, P1 star sigma, M star sigma, and P2 star sigma, where P1, M, and P2 are these maps. We'll start at Klein 4. We can either project onto the first factor, apply the multiplication map, or project onto the second factor. And from there we can apply sigma. The regular representation of Klein 4 is then rho K, which is 1 plus P1 star sigma plus M star sigma plus P2 star sigma, where again, 1 is the trivial representation of Klein 4. We'll also be talking about the Quaternions. It also has sign representations. They're the pullbacks, P1 star sigma, M star sigma, and P2 star sigma, where these representations are pulled back along the quotient from Q8 to Klein 4. And we're going to be using the same names as those for Klein 4. We then have that the regular representation for Klein 4 is rho Q8, which is rho K plus H, where H is the 4-dimensional irreducible representation of Q8. Since we're talking about genuine G spectra, of course, we want to talk about their homotopy. The homotopy of a genuine G spectrum takes the form of what's called a Mackey functor. So a Mackey functor M, and they're always going to be underlined, so M underline, for some finite group G is abelian groups M sub H. For every subgroup H of G, and then for every K contained in H, we're going to have maps. So we'll have M sub H at the top, M sub K at the bottom. Maps going down are called restrictions. Maps going up are called transfers. And they satisfy the double coset formula. And then we also have a Weil group action at each level. And we represent Mackey functors pictorially using Lewis diagrams, which is what I've drawn here. Let's get a couple examples of those, or a lot of examples actually. So first up, C2. We have a C2 mod C2 at the top and a C2 mod E at the bottom. First up is the constant Mackey functor Z. It has a Z in each spot, and the Weil group actions are trivial. The restriction is the identity, and the transfer is 2. One thing we really like to do in topology is dualize objects. So of course we want to talk about duals of Mackey functors. So we have the dual to the constant Mackey functor Z. And how we dualize Mackey functors is that we swap the restrictions and transfers. So now in Z dual, the restriction is 2 and the transfer is 1. Next is the constant Mackey functor F. It has an F2 in each spot. The restriction is the identity, and the transfer is 0. And you can see here, I did not draw an arrow for the transfer because it is 0. So throughout, if an arrow is missing in the Mackey functor, that means the map is 0. Next up is G with an F2 at the top and a 0 at the bottom. So again, the restriction and transfer are both 0, which is why they are not listed. And then if we swap that F2 and 0, that Mackey functor is called little f. The Lewis diagram for Klein 4 gets a little bit more complicated. So we'll have a K mod K at the top, a K mod L, a K mod D, and a K mod R in the middle, where L, D, and R are the left, diagonal, and right subgroups of Klein 4 respectively, and then a K mod E at the bottom. Of particular importance is the constant Mackey functor Z over any finite group that you choose. So again, there's a Z in every spot. All of the Weil group actions are trivial. All of the restrictions are 1, and all of the transfers are 2. One thing we can do is kind of combine Z dual and Z into this Mackey functor called Z10. So again, all of the Weil group actions are trivial, but now at the bottom we look like Z dual, and at the top we look like Z. And then we have this Mackey functor called M because it looks like an M, where we have an F2 in the 4 upper spots and a 0 at the bottom, and then our non-trivial restrictions are the identity. For C4, we'll have a C4 mod C4 at the top, a C4 mod C2 at the bottom, and a C4 mod E in the middle, and then a C4 mod E at the bottom. And then we have the constant Mackey functor Z. Again, Z in every spot. Weil group actions are trivial, restrictions are 1, transfers are 2. And then whenever I have a Mackey functor that is a single F2 at the top and zeros everywhere else, that Mackey functor is going to be called G. So if I refer to G, it could be over C2 or Klein 4 or C4. It will be apparent by context. And then finally, the most lovely Lewis diagram of all of these groups is for the Quaternions. And just a note, I will refer to Klein 4 as K or K4 and the Quaternions as Q or Q8 interchangeably throughout the talk. So for the Quaternions, we have a Q mod Q at the top, and then a Q mod L, Q mod D, and Q mod R, the next level. L, D, and R are the 3 C4 subgroups of Q8, which correspond, and the names correspond to the particular quotient from Q8 to Klein 4. Then we have a Q mod C2 and a Q mod E. So like Z10, we can have this Mackey functor called Z21. At the bottom, it looks like Z. In the middle, it looks like Z dual. And then at the top, it looks like Z again. And then there's this lovely MGW, which will show up briefly in the very last example. So I've included it so you know what it looks like, but it is not particularly important to understand what all of the maps are. It's just a fun looking Mackey functor that will show up once. All right, now of particular interest with the slice filtration is determining slices of Eilenberg-MacLane spectra. So HGM is the Eilenberg-MacLane spectrum with homotopy Mackey functors, m in degree 0 and 0 otherwise. So just like an Eilenberg-MacLane space, but now it's a spectrum. So for example, for C2, we could have HC2Z or HC2F. We could have HKZ10 or HKM, any of the Mackey functors that we've seen already. All right, that's the background. Now let's get to the theorems and definitions, and we'll start off by defining the slice filtration. So we're going to take tau at least NG, contained in the category of genuine G spectra, to be the localizing subcategory generated by G spectra of this form, where H is a subgroup of G, rho H is the regular representation of H, and K times the order of H is at least N. And we're going to write X at least N to mean that X is in tau at least NG. Now, what does spectra of this form mean? Well, SK rho H is a representation sphere for H. Smashing with G over H induces that sphere up to G. Yes, yes it is. So row H is the regular representation of H. And then finally, we take the suspension spectrum. Now, what is a localizing subcategory? It is a full subcategory closed under a number of constructions of particular importance, cofibers, and extensions. It's important to note that a localizing subcategory is not closed under desuspension or fibers. So for example, if we take tau at least 0e, that's the category of connective spectra, which is very much not closed under desuspension or fibers. We get a lot of nice tools with localizing subcategories. For example, we get a localization functor, p lower star from genuine G spectra to tau at least star G. Natural maps from p lower n plus 1 to p lower n. And then also cofiber sequences, p lower n plus 1 of x to x to p upper n of x for some genuine G spectrum x. It's important to note that Hill, Hopkins, and Ravenel use the original or classical slice filtration. Today we're using the regular slice filtration from Ullman. All of the results are the same except for an indexing difference of 1. I've already given you a definition of x at least n, so of course I have to give you a definition of x no bigger than n. So we're going to say that x is strictly less than n if the H equivariant maps from sk row H plus r to x are 0. For every r at least 0, every subgroup H of G, and for every k such that k times the order of H is at least n, i.e. there are no maps from generators of tau at least ng. Now, if we have for some G spectrum x both x at least n and x no bigger than n, we call x an n slice. And what we're really interested with the slice filtration is finding out slices and what they are. So we're going to take some spectrum x and ask, is this a slice? If yes, that's awesome, we're done. If not, then we want to decompose x into its slices, into its building blocks, and see how they fit together. A couple of useful propositions for later. First up is due to Hu-Krij. We're going to take n to be a normal subgroup of G, and then Q from G to G mod n is the quotient map. Then if we take some G mod n spectrum x and some G spectrum y, we have a natural equivalence. We pull back x and smash with y and take the n fixed points. That is equivalent to taking the n fixed points of y and smashing with x. And this is something I'll refer to as the projection formula. Another useful proposition due to Zheng is if we have some Mackey functor M and it is an HGZ module, then for any H contained in K contained in G, if we restrict from H to K and then transfer back up from K to H, that has to be multiplication by the index of K in H. All right, that's the setup we need. So now we're ready to talk about pullbacks and slices. We're going to start with N, a normal subgroup of G. And we have various pullback or inflation. And when I say pullback and inflation, those are synonymous. So we have various pullback constructions to produce a G spectrum from a G mod N spectrum. First up is the ordinary pullback, Q star, which is left adjoint to the N fixed points functor. There are some nice things about this functor. There are some bad things about it. For example, if we pull back the sphere spectrum, we get the sphere spectrum. That's something we want, that's awesome. However, it doesn't play well with the slice filtration and the inflation or pullback of an HG mod NZ module does not have canonical HGZ module structure. For example, let's take a look at how it doesn't play well with the slice filtration. So HEZ is a 0 slice. It's an Eilenberg-MacLane spectrum with homotopy concentrated in degree 0. Now, if we use the projection formula, the fixed points of the pullback are HEZ smashed with the G fixed points of the sphere spectrum. i.e. the homotopy of this pullback is the homology of the fixed points of the sphere spectrum. But that's very complicated and not concentrated in degree 0, i.e. this pullback is not a 0 slice. So Q star does not necessarily play well with the slice filtration. As for the module structure problem, let's take G and N to be C2 so that the quotient is E. And now we want to ask ourselves, if we pull back HEZ, is that an equivariant HC2Z module? Well, it's pi 0 is a Z plus Z at the top and a Z at the bottom. And we can see we have the Z plus Z using the projection formula. So if we take the C2 fixed points of smashing with the sphere, well, then we get HEZ smashed with the C2 fixed points of the sphere. But the C2 fixed points of the sphere is S0 wedge, the suspension spectrum of RP infinity. That's where we're getting the Z plus Z from. And then the Z is because our underlying spectrum is HEZ. Now remember that restriction and transfer proposition, our group is C2. If we go down and then come back up, we need to get multiplication by 2. But there is no way that that composition is 2. Therefore, we do not have an HC2Z module. Next up is the geometric inflation functor, phi star n, which is right adjoint to the geometric fixed points functor. What's really nice about it is that it plays well with the slice filtration. If we take the k slice of x and pull it back, well, that is the dk slice of the pullback of x, where the order of n is d. A really awesome tool. If we have a slice for a quotient group, we pull back that slice to our group and we still have a slice. And we know exactly what kind of slice it is. Unfortunately, it has the same module structure problem. So if we pull back HEZ to C2, well, we get HC2, the pullback of Z, and that pullback is this Mackey functor. It's called a geometric Mackey functor because there's one thing at the top and zeros everywhere else. And again, there's no way that the composition of the restriction and the transfer is multiplication by 2. So again, we do not have an HC2Z module. Finally is the Z module inflation functor, psi star n. And it's left adjoint to the n fixed points functor. The really awesome thing about this functor is that it fixes the module structure problem. If we pull back Hg mod nz, we get HGZ. This is great. We want this sort of thing. We want to pull back our nice constant Mackey functor and get another constant Mackey functor, or rather spectrum with homotopy constant Mackey functor. But there's a trade-off. It doesn't usually play nice with the slice filtration. So for example, if we take the n slice of HKZ and pull that back, we do not necessarily get the n slice of HQZ. So for example, when n equals 7, the 7 slice of the 7 suspension of HKZ is a rho k plus 3 suspension of HKZ. Now when we inflate this spectrum, we get a rho k plus 3 suspension of HQZ. But the 7 slice of sigma 7 HQZ is a rho q minus 1 suspension of HQZ dual. And these two spectra are very much not the same thing. Now, sometimes these three constructions agree. For example, if your underlying spectrum of your G mod n spectrum X is contractible, well then Q star aligns with phi star. So here's a slightly dense looking proposition, which we will see examples for in a moment. We're going to take n to be at least 0 and capital N to be a normal subgroup of G with the order of n is D. Now M will be a G mod n Mackey functor, and let's let it be a module over Z G mod n. And now when we take our the sigma n of h g mod n m, and then take the n slice and pull it back using Q, suppose that it has no slices in dimensions greater than d times n. Well, then the non-trivial slices of sigma n h g psi star m above level dn. So here's the pullback of the psi star pullback of our spectrum. The dk slices are the q star pullback of the pk slices of our original spectrum. But those are also the phi star pullbacks of the k slices of our original spectrum for k strictly greater than n. So this is an instance where our three pullback constructions align to give us slices of a pullback. That's a lot of words, so let's take a look at some examples. So how about G equal to C4 and N equal to C2? Now let's take the tower for sigma 5 HC2 F2. This spectrum has a 6 slice, sigma 3 HC2G, and a 5 slice. The 2 row C2 plus 1 suspension of HC2 little f. Now if we apply psi star, this co-fiber sequence becomes this co-fiber sequence. It gives us the upper half of our tower. So the threefold suspension of HC2G becomes the threefold suspension of HC4G. This is an instance where psi star actually aligns with phi star because the underlying spectrum of HC2G is contractible. And then this spectrum here inflates to the spectrum, even though they don't quite look the same. That just has to do with some equivalences and suspending things. All right, now, that proposition didn't tell us anything about level n. So here we have level n. Does it inflate to a slice? Not necessarily. So when we inflate our co-fiber sequence, our 5 slice turns out is no longer a 5 slice or any slice. So we found the upper half of our tower, but then the work is not done. We have to decompose this spectrum into its slices. And it turns out that it has 2 slices, an 8 slice, which is a 2-fold suspension of HC4G, and then a 5 slice, which is a 3 plus sigma suspension of HC4F. All right, let's up the difficulty a little bit to the Quaternions. So we'll take G to be Q8 and N to be C2. Now Q8 mod C2 is Klein 4. So we want to look at the tower for towers over Klein 4 and then pull those back to Q8. So if we take sigma 7 HKZ, here's its tower. It has a 12 slice, a sigma 3 HKG, an 8 slice, a row K plus 2 suspension of HM, and then a 7 slice, which is a row K plus 3 suspension of HKZ. All right, now when we apply psi star, our sigma 3 HKG becomes a sigma 3 HQG, and our 12 slice becomes a 24 slice because the order of C2 is 2. Our 8 slice becomes a 16 slice, and we get a row K plus 2 suspension of H phi star C2M. So here's another instance of where psi star and phi star align. We're inflating with psi star, but the underlying spectrum of M is contractible. It's got a 0 at the bottom of our Mackey functor. Therefore, the 2 pullbacks agree on the spectrum. And then our 7 slice, this row K plus 3 suspension of HKZ, well, that becomes a row K plus 3 suspension of HQZ. And the proposition doesn't tell us anything about what happens in degree n. So we have this lovely 7 slice, but when we inflate it, it's no longer a slice. So then we want to play the game. Okay, what are the slices of this spectrum? And it turns out its 8 slice is a row K suspension of that lovely, of HMGW, where MGW was that lovely Mackey functor from the before. And then it has a 7 slice, which is a row Q minus 1 suspension of HQZ dual. So the really nice thing about these constructions and this proposition is that if we have a tower or slices for a quotient group, well, that's easier because it's a smaller group. Then we can apply psi star, and then we get the top half of our tower. We get a good chunk of the slices for our group, which then reduces the work because we have less slices that we need to find. And that is all I have for you today. Thank you for coming.